Okay, we'll look to finish up section 5.3 in this video. We're talking about the fundamental theorem of calculus, and there's a part 1 and part 2 of that. We looked at part 1 in the previous video, and so I'll talk about part 2 in this one. So far, we have computed integrals as the limit of a Riemann sum, either using right endpoints or left endpoints. Okay, this procedure is sometimes long and difficult, so the fundamental theorem of calculus part 2 is going to provide a simpler method for evaluating integrals. So here's what the fundamental theorem part 2 says. If f is a continuous function on a closed interval ab, and capital F is an antiderivative of little f on that interval, then the definite integral going from a to b of f of x dx is capital F of b minus capital F of a. In other words, all we have to do is take the antiderivative, plug in the upper bound into the antiderivative, and then subtract the antiderivative evaluated at the lower bound. Okay, and here's a proof of that. Let's let g of x be the definite integral going from a to x of f of t dt. By the fundamental theorem of calculus part 1, g prime of x is equal to f of x. Okay, we looked at that in the last video. Okay, the fundamental theorem part 1, g prime of x is equal to f of x. And so g is an antiderivative of f. Therefore, we're going to let g of x, at capital F of x be equal to g of x plus some constant. Okay. Remember that the derivative of a constant is always 0. Okay, so g prime of x would be equal to little f of x. Okay, capital F is the antiderivative of little f. Then capital F of b minus capital F of a would be g of b plus c minus g of a plus c. The constants would cancel there, and so we are left with g of b minus g of a. Now here's, where are we at here? Here's g of x. Okay, g of b would be the integral going from a to b of f of t dt. G of a would be the integral going from a to a of f of t dt. The integral going from a to a of f of t dt, that'd be 0, right? You're just creating a vertical line in that case, so the area would be 0. And that leaves us with the integral going from a to b of f of t dt. All right, but that's what I had to show. I had to show that when you integrate a function with bounds here, you're going to just simply get the antiderivative, okay, and then plug in the upper bound into the antiderivative, and then subtract the lower bound evaluated at the antiderivative. Okay, way quicker and easier than using the limit of a Riemann sum. So let's take a look at some examples. Suppose that we want to integrate going from 0 to 2 the function x squared dx. Okay, well the antiderivative, you'd use the reverse power rule. You're going to add 1 to the power, divide by the new power. So the antiderivative of x squared would be 1/3 x cubed. Okay, now here's some notation. This bar that I've got drawn to the right is a necessary thing when you have a definite integral. We call this the evaluation bar. We're going to be evaluating 1/3 x cubed going from 0 to 2. Now you always plug in the upper bound first, lower bound second. Don't get that mixed up. So when I plug 2 into the antiderivative, I'm going to have 2 cubed divided by 3, and then when I plug in 0, I'll be subtracting 0. 8/3 is the answer. A lot easier than computing the limit of a Riemann sum. Okay, here's another example. Okay, how about if we want to integrate the function 1/2 x cubed minus 3x plus 2 going from 2 to 4. Okay, well you can split up an integral into several integrals and bring out the constants. As long as you're adding or subtracting, that would be okay. Never ever if you're multiplying or dividing though. Okay, so that's what I've done. I split this into 3 integrals and brought out the constants, and now I'm ready to get the antiderivatives. The antiderivative of x cubed would be x to the fourth over 4. Antiderivative of x is x squared over 2. Antiderivative of 2 would be 2x. Now make sure that when you calculate the antiderivative that you lose the integral sign. Okay, also the dx. That should no longer be there once you have found your antiderivative. Now make sure that your evaluation bar is there, okay, in the case of a definite integral. So I'm evaluating each one of these expressions going from 2 to 4. Now I'm going to plug in my bounds. So when I plug 4 to the fourth divided by 4 is 4 cubed, that'd be 64. Minus, when I plug in 2 to the fourth is 16, divided by 4 is 4. Okay, I want 1/2 of that whole thing. Minus 3 times the quantity, okay, when I plug in 4 here, 4 squared is 16, divided by 2 is 8. Minus, when I plug in 2, 2 squared is 4, divided by 2 is 2. Plus, when I plug in 4, 2 times 4 is 8, okay, and then minus, when I plug in 2, 2 times 2 is 4. Simplify this, you're going to have 30 plus 18 plus 4 is 16, and 16 would be my answer. Okay, here's another one. Suppose that we're going to integrate the function 5u plus 1 times u minus 2 going from 1 to 3. I've mentioned this already just before we do this problem. Make sure that you're writing dx or du or dt or whatever the variable of integration is. If you don't have that written, I will take points off. If you don't have the integral sign, I will take points off. If you don't lose the integral sign once you've got the antiderivative, I'll take points off. Notation is important. Okay, make sure that you're using good notation, just as we've been doing, all semester here. Now, before I find the antiderivative, of course, I can't split this integral into two integrals. Again, I can only do that if I'm adding or subtracting the terms, never ever if I'm multiplying or dividing. But let's go ahead and FOIL out the integrand. Okay, and we get 5u squared minus u minus 2. And now we're ready to get the antiderivative. Of course, I can split this, like I did in the other problem, although I don't need to do that. Okay, I can just, I know I'm getting the antiderivative of each one of these terms individually. So why don't we just go ahead and do that? 5 is a constant, you're going to leave that as is. Antiderivative of u cubed would be, or u squared rather, would be u cubed over 3. You're going to add 1 to the power, divide by the new power. Minus 9 times the antiderivative of u would be u squared over 2, and then minus the antiderivative of 2 would be 2u. We are evaluating this from 1 to 3. So now when I plug in my bounds, plug in 3 first. 3 cubed is 27, divided by 3 is 9, times 5 is 45. When you plug in 3 into the second term, 9 times 9 is 81, divided by 2. Okay, and then minus 2 times 3 is 6. And then minus the quantity. When you plug in 1, you're going to have 5/3 minus 9/2 minus 2. Be sure to include parentheses around that since you're subtracting the whole thing. Okay, and when you simplify, you should be getting 10/3. Another thing to note here, make sure that you're giving your answers in exact form. Okay, that's how the book will want it, that's how WebAssign will want it, that's how I'm going to want it also. Okay, exact answers. Here's another example. Okay, suppose that we want to integrate cosine theta over the interval pi to 2 pi. Okay, well the antiderivative of cosine theta is sine theta, and we're evaluating sine theta from pi to 2 pi. Plug in the bound. Sine of 2 pi is 0. Sine of pi is 0. 0 minus 0 is 0. Okay, now why is the answer 0? Well, here's a picture of the cosine curve on the interval pi to 2 pi. Now these two shaded regions are the same size, but one region here to the left of 3 pi over 2 is below the x-axis, and the other region is above the x-axis. Okay, so of course the region above the x-axis would indicate a positive number, the region below would indicate a negative number. When you add these together, they offset each other, going to give you 0. So my answer here is not really, you know, I wouldn't take away anything in terms of area under the curve from this calculation. Okay, and of course another thing to note here is that, you know, we are describing a definite integral as area under the curve. There are many applications of the definite integral, okay, not just area under the curve. You guys will see that, you know, as you continue on in the book, you know, we'll see some applications here, but you'll be doing a lot more with applications of integrals in Calc 2. So just take note of that. Here's another example. Okay, let's integrate e to the x plus 2x plus 1 over the interval -1 to 2. Well, the antiderivative of e to the x would be itself e to the x, plus antiderivative of 2x, that'd be 2x squared divided by 2, the 2's cancel. I'm going to leave you with x squared. Antiderivative of 1 is x. You're evaluating that from -1 to 2. Plug in the bounds. When you plug in 2 first, you're going to have e squared plus 4 plus 2. That should be a 2 there. And then minus the quantity. When you plug in -1, you're going to have e to the negative first plus -1 squared is 1. And then plus -1. I'm going to go ahead and change, this should be a 2. Sorry about that. Okay, and then combine your like terms. You're going to have e squared minus 1 over e. 4 plus 2 is 6. And let's see, 1 minus 1 is 0, so it should be e squared minus 1 over e plus 6 should be the answer. Sorry about that. Okay. Let's take a look at another one. And again, just leave that in exact form. Take a look at another one here, and suppose that we want to integrate the function 1 over x on the interval 3 to 6. Okay, the antiderivative of 1 over x is the ln of the absolute value of x. Now, in this case, you don't actually need absolute value bars since 6 and 3 are both positive numbers. However, I just make it a habit of including them. Okay, sometimes there's exceptions where you'd actually don't need them. Okay, here would be one of them, but there's no problem with having them there. Okay, now if my bounds were different, like if I were going from like -3 to -1, then I would want the absolute value bars because I can't take ln of a negative. Okay. Also, if I were going to find the what's called the indefinite integral or the general antiderivative, I must have the absolute value bars, otherwise it's the wrong answer. Okay. Let's plug in the bounds. So you're going to have ln 6 minus ln 3, or ln of 2 would be that number written as a, using a single logarithm there. And again, exact form. Okay, now what's wrong with this calculation? What if I were to compute the integral going from -1 to 3 of 1 over x squared? Well, 1 over x squared, that's the same as x to the negative second power, right? And I can use the reverse power rule, add 1 to the power, divide by the new power. So you're going to have x to the negative first divided by -1, or that'd be -1 over x. Plug in the bounds into -1 over x. When you plug in 3, you'll get -1/3, and then minus 1 gives you -4/3. Now, -4/3 would be the wrong answer. The reason is because this function is not continuous on the interval -1 to 3. Okay, I would have a vertical asymptote at x equals 0. So the point of this is to say, don't just blindly compute an antiderivative and plug in the bounds. If I were integrating, let's say, from -3 to 6 in this problem, well, that's not possible, right? Because I've got a vertical asymptote at x equals 0. Okay, that integral would not exist. Now, in Calc 2, you guys are going to learn about what's called improper integrals, and there's a couple of types of improper integrals, and you'll talk about how to handle situations where there's a vertical asymptote, let's say, on the graph, and still performing an integral calculation. All right, here'd be another one. Suppose that we want to integrate the function t minus 4 times the square root of t dt on the interval 0 to 4. Okay, well, we've seen sometimes with derivatives, you want to simplify first and then differentiate. Same deal with integration. Sometimes you want to simplify first and then integrate. So I'm going to go ahead and distribute the square root of t into these two terms. T times root t would be t to the 3 halves, and then minus 4 times would be t to the 1 half. Now I can use the reverse power rule on these two terms. Okay, add 1 to the power, divide by the new power. You're going to have t to the 5 halves divided by 5 halves. That's the same as 2 fifths. Minus 4 times t to the 3 halves divided by 3 halves. That's the same as multiplying by 2 thirds. Make sure that you lose the integral notation and the dt there. And we're evaluating this from 0 to 4. So now when I plug in my bounds, 4 to the 5 halves. Okay, well, 4 to the 1 half would be 2. Square root of 4 is 2. 2 to the 5th is 32. Times 2 is 64, divided by 5. Okay, minus 4 to the 3 halves. Well, 4 to the 1 half is 2. 2 cubed is 8. Times 2 is 16. Times 4 is 64, divided by 3. 64 fifths minus 64 thirds is negative 128 over 15. The fact that that's a negative means that this function is negative on the interval that was given here, 0 to 4. Okay, here's just a quick sketch of the graph of this curve, t minus 4 times the square root of t. On the interval 0 to 4, you can see the entire curve is below the x-axis there, and therefore we get a negative. When you are working with integration and you get a negative, be sure that you realize why that happened. Okay, like in this problem here, I'd have a wrong answer. Okay, but this problem here, it's because the entire curve is below the x-axis. Okay. If more of the curve is below the x-axis than above the x-axis, your answer will be a negative. Okay. Here's another example. Let's try the integral going from 1 to 2 of 4 plus u squared divided by u cubed du. Okay, well, I'd want to simplify first. Let's go ahead and split this into two fractions. So I've got 4 over u cubed plus 1 over u. And 4 over u cubed, that's the same as 4 to the negative third. I'll leave the 1 over u as is. And I can apply the reverse power rule on this first term. Add 1 to the power, divide by the new power. Okay, so you're going to have 4 times u to the negative second divided by negative 2. 4 over negative 2 is negative 2. Negative 2 u to the negative second would be that first term there. Antiderivative of 1 over u is the ln of the absolute value of u. And here's be another situation where I actually don't need absolute value bars because 2 and 1 are both positive numbers when I plug them in. When I plug in 2, okay, negative 2 divided by 4 is negative 1 half. I'm adding the ln of 2, and then when I plug in 1, it's going to be a minus the quantity negative 2 plus ln of 1 is 0. Negative 1 half plus 2 is 3 halves, so 3 halves plus the ln of 2, that would be the exact answer there. Okay, here's another one. We have the integral going from 0 to 2 of the absolute value of 2x minus 1 dx. Okay, the first thing that you'd want to notice here is that when you apply the definition for absolute value as a piecewise definition, you're going to have, in this case, 2x minus 1. If 2x minus 1 is greater than or equal to 0, that would mean that x is greater than or equal to 1 half. And then we want the opposite of 2x minus 1 if 2x minus 1 is less than 0, or x is less than 1 half, same thing. Okay, now 1 half is between these two numbers, 0 and 2. So I'd want to begin the calculation by splitting this integral at 1 half. And I've done that. We'll find the area under the curve going from 0 to 1 half first, and then whatever that is, we'll add the rest of the area starting at 1 half and going to 2. That way we'll get the total area going from 0 to 2 underneath this curve. Well, if I'm going from 0 to 1/2, then x is less than 1/2, right? The bounds are in terms of x here, so I want the absolute value of 2x minus 1 to be represented as negative, the quantity 2x minus 1. Okay. If I'm going from 1/2 to 2, then x is bigger than 1/2, so I'd want to be using piece 1, where I just write 2x minus 1. Okay, and then I can get the antiderivatives here. You're going to have negative 2x squared divided by 2. The 2's cancel. That'd be negative x squared plus x. Okay, and then plus the antiderivative of 2x. It would be 2x squared over 2. The 2's cancel. And then minus x. Of course, make sure that your evaluation bar is there with the bounds. And you can plug in the bounds. And I'm getting 5/2. Okay, now of course in a problem like this, using the definition for the piecewise definition for absolute value is a necessary thing. Okay, we had to do that in the calculation here. Here's one more example. So this was a problem that we had looked at earlier when we had done the fundamental theorem part 1. If I were to just show you that problem again, here's we did that. Okay, and let me just show you how to do this problem using the fundamental theorem part 2. So this is a definite integral. I can use the fundamental theorem part 2. Antiderivative of cosine t would be sine t. I'm evaluating this from pi over 2 to x cubed. Plug in the upper bound first, lower bound second. Sine of pi over 2 is 1. Okay, so now when I differentiate sine of x cubed minus 1, derivative of the constant is always 0. The derivative of sine of x cubed, that'd be a chain rule, right? You're going to have cosine of x cubed times the derivative of x cubed, that'd be 3x squared. Well, that is exactly the same thing that we got when we got the fundamental theorem part 1. Okay. We'll be using the fundamental theorem part 2 all over the place to finish out the course. Okay, make sure that you get some practice with that. Here's some homework on page 399. And we're going to continue to talk about the fundamental theorem part 2 actually in the next section a bit more, just for some more practice.